What are vectors? Let's just give an intuitive definition of vectors as being just an array of numbers, of real numbers. We see here examples. This array, this column vector, array with 2 numbers, an array with 3 numbers, and the array of variables. So x, y, and z could be any real number. What can we do with vectors? Well, the short answer is linear combinations. But what are these linear combinations? First of all, linear combinations can be viewed from 2 points of view. The first one is analytical, meaning we just look at the formula, you do calculations with it. But the second point of view is geometrical. Let's just focus first on the analytical point of view. I give you an example here. We find here 2 vectors, u and v. So u and v are just abbreviations for the column 1, 3, and v is an abbreviation for the column 1, minus 1. Again, an array of numbers with 2 entries. We are here multiplying the u vector by the scalar, the number 2, and here multiplying the vector v by 4. And then we sum these two things. Okay? How do we do this calculation by hand, meaning analytically? Well, first we write u and v, as you see here. Second, we multiply each entry by the number here. So 2 times the vector u is 2, 6. 4 times the vector v is 4 minus 4. You just multiply each entry by the number. And then you sum entry-wise. Can you see? The end result is 2 times 1 plus 4 times 1. And then 2 times 3 plus 4 times minus 1. You just sum element-wise the 2 vectors. Notice in this picture that I'm summing vectors of the same shape, meaning 2 entries. You cannot sum a 2-entry vector with a 3-entry vector. Now, this basic example of linear combinations motivates us to make a general definition, an analytical definition of linear combinations. So instead of just summing 2, let's assume that we have k vectors. So u1 through uk, all of them living in Rn, which means that u1, for example, has n entries, and uk has, again, n entries. Can you see? Before, we saw the case when n is equal to 2. And we saw 2 vectors, u1, u, and v. But this time, we just assumed we have an integer number k of vectors. It could be, for example, 3 vectors. I want now to construct a linear combination of these k vectors. Well, to do that, I need k numbers. So I multiply each vector in this list by a real number, and then I sum everything. You have, for example, the number c1, a real number, multiplying u1. Of course, you sum c2 times u2, and so on, and ck, uk. Of course, this is a long expression, so we usually introduce abbreviation. Is to write the summation from I is equal to 1 up to k of cy ui. Now, let's see this geometrically. What does it mean, a linear combination from the point of view of geometry? Let's see. We use the parallelogram rule. We find here 2 vectors, one in yellow with coordinates, you see, on the horizontal axis 1 and on the vertical axis 3. We see also here a pink vector whose coordinates is 1 for the first one along the x-axis, and along the vertical axis it is minus 1. I want now to do the following linear combination. 2, 1, 3 plus 4, 1 minus 1. What does it mean to twice the vector 1, 3? Well, you see here is a vector that goes from the origin up to this point here. So it's twice as long as the vector that goes from here to here. What does it mean 4 times this vector? Well, this is the pink vector here, 1 minus 1. 4 times, well, is the vector that goes from here up to here. So this vector here goes from here to here, and this vector here goes from here to there. And now you want to sum those. And I don't know if you remember, but to sum two vectors from the geometric point of view, we use the parallelogram rule, which means simply you just construct a parallelogram that you see on the picture. So you have this side of the parallelogram, you have this side of the parallelogram, and now you just build the other ones, which are parallel. So this side is parallel to this side, and this side is parallel to this side. Of course, the result of the summation is the green vector. Another way to look at this parallelogram rule is again to imagine ourselves at the origin, and now we have to move in two-dimensional space. First, we move twice this quantity, this vector, so we move from here to here. But now that we are here at this position, you want to move 4 times 1 minus 1, which means this much, this much, this much, and this much. So you end up here at this point. So the displacement vector is how much you moved, which is the green vector.